let me try to copy it on that disk on a thumb drive, and then we can pass it around. Yeah, just a floppy. That's right. It's not quite. Doesn't want to flop, but let's see. There. Why is Okay, there's a workshop folder. Just copy that over. I hope. See it?
Yeah, workshop.
Okay, workshop.
Workshop.
Yeah, workshop folder. Just copy the entire folder over to your computer. Yeah, and there are two zip files in it. Unzip them, and then you can. Okay, we're up. All right. Okay. Yes. That's. Let's see what we can do. The original intent of this workshop is that you guys work. Okay. But in case there's okay, one thing is that I like people who have projects to come up and tell us what he want to do, what kind of CPU he want to design, and if there's any progress, or let us know. So that's one thing. We probably can go around and introduce ourselves, and maybe talk a little bit about what you want to do. And we got lots of people online to entertain. So we have I have several topics that I want to talk about, if you allow me. And then I think people may have problem using the Bravia 2 board. Then we can talk about it, go around. I think somebody have experience using it, and we can help each other if there's any problem. You know, the tool chain, the IDE, the Diamond IDE is very complicated. So you have to spend time, you know, play with it, and to maybe do some simple things, simple tutorial examples, get yourself familiar with it, so you know how to write something in the VHDL code, VHDL file, open a project, and get it synthesized, get it simulated. Okay, and so that's the these are the very hard part, especially if you are not familiar with the VHDL language and also the IDE itself. And the IDE has lots of components. So of course there's an editor in it. Everybody can get along with that, no problem. But then it's the how to open up a project, how to get the VHDL file synthesized, and how to use the simulator to look at the signals. And then the most crucial part is, of course, to generate bitmap image that you can download into the FPGA chip. And that would, once you get that design download into FPGA chip, the board has power, the board has I/O, the board has a 50 megahertz clock. So all these things you can include in your design to have a circuit running. Okay, once you get that circuit running, how do you know it's running? How do you know it's running correctly? Well, that has lots of things. For example, what in my in my design, what I want to do is always put a fourth kernel in the design, so that when you download it and reset it, it starts to run. The fourth program, and then if it runs correctly, it will say okay, and that's really the goal to reach that stage. Because this morning I'll show you Rick Collins. He gave me a Testbench presentation, so I will run that Testbench presentation. He's doing it the standard way, the traditional way. The traditional way to do any design, any circuit design, once you have the VHDL files for the design, you have to write a test bench. And this test bench would verify your design. And to write a test bench, it is more difficult than writing the device itself, because the test bench kind of enclose your design in a bigger environment, which generate the proper signals to drive your device. And then the device will respond, and the test bench would take the response and verify to see if the response is correct. If it's not correct, there's a problem in the design. So if you test bench is a much more difficult job. So I think I have taken an easier approach in that I wrote the E4 and have it run. Okay. The fourth program doesn't use the entire chip. Many instructions fourth does not use. So this instruction doesn't get tested. So a E4 system is not 100% verification tool, like if you would do a good test bench. So so that's one topic. Another topic is I did the 8080 implementation, and I distributed them so that everybody, at least you should get that 8080 design running on the board. Okay, so that's the you don't have to know anything about it, but you just have to go through the process of clicking the right buttons to get the thing synthesized, get the layout. Well, there's all these chip design terms. I'm not still quite fluent in them. But you generate the bit image, you download it into your FPGA, and then you should be able to see the fault running. Okay, so and so the 80, I've talked about 8080 a number of times. So I think I may not, unless if you have any problem, we can talk about it. But recently, I started to do the PDP-1. Okay, so that's the first mini computer there is, and so I was trying to review all the architectures since the very first electronic computer, and so from the von Neumann computer down to ARMS. So, you know, a couple of weeks ago, I said, well, I got 8080, but I should do one of these classic architecture. And which one? Okay. And then I was searching through and looking at one video presentation, a 2-hour video presentation from the Computer History Museum. I think it was a couple years ago when they finished restoring PDP-1. And they have a big panel discussion. They invited the original designer of PDP-1 from at that time the DEX early employees, and then lots of users at the time, mostly in MIT, because DEC built the first PDP-1 and gave it to MIT. So it is a big cabinet, a refrigerator. Yes, a refrigerator. Okay. So, and the story was that they gave the PDP-1 to MIT. So all the people in MIT started programming it. They don't have a manual. They don't have any instruction. So the MIT students or the teaching staff start to generate the assembler, the compiler, the editor, and all kinds of things. And DEC just took all the demo programs and then show it off in trade shows. So, so I was very impressed with that video panel discussions. So I said, okay, I'll do PDP-1. Okay. So I started, and wrote the VHDL code, or the compiler, the synthesizer, and then have to write a forth for it. So that's not very hard, because Chuck Moore gave us an assembler for the MUP21, and I'm using his assembler to assemble force for various processors, mainly the EP16, P8, and the EP32. So I have that assembler. So I just modify that assembler, and it assembles the PDP-1 code. So I have a full system for it. And yesterday, I started to get the eForce image loaded into the design. And then the simulator starts to execute the instructions. Okay, I think I verified 4 instructions. That's as far as my progress. But I think things would work. Just have to debug the instructions one by one. So I'll talk a little bit about that too. Okay. Okay. The first thing, not this one, but the test bench. Okay. So this is by the Ray Collins. So he took the 8080 design and actually ran the design, and I think he was successful in getting it to work. But he's a very experienced chip designer and chip. So he has the deep knowledge about the Testbench. So he actually wrote a Testbench for the 8080. And he told me that you got one instruction wrong. Okay. And of course, because that instruction was I was not used. I didn't use the instruction, so I didn't check it out. So let's. He also gave me this presentation, and I don't fully understand it, but I'll read it for you. Okay. So the Testbench facility, it includes functional testing, automated testing, repetitive testing, and requirement testing. These are all the formal testing procedures you have to go through to verify that you have a correct design. So functional testing, you have UUT, the unit under test. It's the piece of design that you have done, and then the test bench. The function of the test bench is to exercise this UUT in all possible ways. So the test bench will generate stimulus to the UUT, and the test bench would also watch over the UUT and verify that it has the correct responses. So you can basically automate the testing if you have well, the stimulus can be generated automatically, exhaustive verification of all possible inputs, Monte Carlo type random verification, and corner case checking. So these are the many different strategies in testing. Of course, we would like to do exhaustive verification. We want to test all the possible pathways inside the UTT. But because you only have limited amount of input that you can impose on the unit, so you may not be able to test it exhaustively. And there are, when you cannot test it completely, you might want to use Monte Carlo type random verification. You just pick up a certain cases randomly and do the test, and hopefully that it will cover all the viable pathways. And corner case checking, particular pathways on the fringe, the limits. These cases you may not always be able to reach, and you can set up corner case checking. These extreme cases that you can set up manually to. So all the responses from the UUT, that means all the output pins, you can receive all the responses and check to see, to verify your design. So repetitive testing, usually I think the computer is in, or electronic device in such design, in such shape, way that if it runs once, usually it will always run. But I think people were worried that if you do many tests, the response may not be the same. And there are cases for that. And so you want to be able to repeat the testing to your own satisfaction. And then once you get bug fixed, you want to retest everything. And if any change, if anything change, you have to retest it. So that the test bench has the advantage. If you write it once, it's always there, and you can always run it when you develop the chip. So requirement testing, and usually if you do the design according to the book, you have a set of requirements. And then these requirements can be expressed faithfully in your test bench. Okay, so you want to design the test bench. You want to design your device according to the requirements, and you want to also design the test bench to see if the device fulfill all the requirements. So you need to design it that way, and you have to verify all the requirements. And if there's a specific features and capabilities of the design, you want to verify all of them. Okay, test bench design, test generation. You can do the algorithmically if you know if the function has a formula. You can implement the formula and test it algorithmically. And it can also be data-driven. If you have, if you cannot generate the data according to a function, you might want to collect a table of data to drive the test bench. And if you have special purposes, you have special input, and you expect certain output, you want to verify all these things accordingly. So you can generate the data using functions, and if that makes a very complicated data patterns. You can generate very complicated data patterns. And the limitation is that if you are using the same algorithm test bench and design, and they tend to agree with each other. So that may not be the best way to verify the algorithm. Okay, some examples which I don't fully understand or appreciate. So the data-driven test generation, if you can collect all the data that you want to impose on the device you can write all the data in an external file. So if you have all this data in a separate file, you can always call this file and do the testing. And then you can test the arbitrary data, and you can also impose timing requirement in it, so that timing can be verified as well. So the CPU, the best testing, the corner case testing can all be done using data-driven tests. So here's you can generate a test signal. You can put these test data even inside the unit, so that usually these are logic-oriented test design. If you want to test small modules inside a unit, and if you want to test a specialized interface, and UART, SPI, loopback testing, and all these things are possible to do in a test bench. So the for the 8080, I think that's what he did for the 8080 design. And data-driven test memory interface, command read from file, one per line, and he could just read the file one line at a time, do the testing, and then do the report if there's if it is satisfactory or not satisfactory. Okay, reset, fetch, write, and read, and these are all the test bench commands. Okay, this is a part of the test bench he wrote for the 8086, and then I think these are just different instructions that he's testing. I don't know what this are these the just address or something. I'm not sure what this. I think this is machine code. This column is machine code. These. Well, I can only read it. Okay, don't ask me hard questions. Okay, here is the explanation. Line 1 is a command, and line 2 reset processor for 2 clock edges, 3 to 9 verify address and supply opcode. Okay, so these are what he's doing in his test bench code. Okay, so he found some problem that this A in and A cell, A select, these two signals are not quite right. Yes. So these are the problem that he found, that these A input select and A select, these signals are not correct. So problem seems to be with A select, which is generated solely for the opcode which is good. So the code generating A cell is suspect. Okay, so that's what he found, the error here. So these two, this one should be ALUA. So here I'm using this, and this is a signal which selects the A select. The A register has a lot of input. So which one do you want? So I'm using the A select to select select one of the input to the A register, and that's a multiplexer. So in front of every register, there's a multiplexer, and this multiplexer accepts lots of inputs, and this A select selects one of them, and this was not correct for the particular instruction. So I'm very grateful that he found it. And it is because I didn't use that. It's an increment-decrement instruction, which I did not use in E4. So I was not aware of the problem. But he's trying to do a fairly exhaustive test. So he's tested every instruction and found that these two instructions produce wrong results. And that's the power of a test bench.
What was the total number of test bed functions? And then how many did you decide to use?
Okay, the E-force, the idea behind the E-force is that to implement a fourth operating system, you need about 30 instructions. That's the virtual, for the fourth virtual machine, you need about 30 instructions. And these 30 instructions has to be constructed from the machine code, okay? Once you have these 30 primitive instructions for the virtual fourth engine, then fourth would run because everything else are in high level. And these high level instructions are portable, okay? So when you move the design into a new machine, you only have to recode these 30 instructions. And so.
But the test bed was we were talking about this column.
Yes.
Exhausted.
Yeah.
You didn't use that much. So you didn't use all of it.
No, I didn't use. It's about, I guess, a third to a half of all the instructions. Okay. And this one, I'm lost. I don't understand it because it's very exotic in that they use all the features in the VHDL, and I haven't got through any of these. For example, I don't understand what assert is, and I really report. Of course, it is type out something out, but these are all the facilities that you use. You see here it is when fetch is an instruction in his test bench. So it encounters a fetch, then it will just read the following data, and then generate a test case and impose it on the CPU, and then read the data back. Okay, so this is it's beyond me. I think we have to get Rick back to talk about it. Okay, it's a good it should be a good lesson for all of us if we really want to do a good job, and if you wanted to do a commercial product, which you want to be, you want to ensure, give your customer the assurance that this design meets their requirement. Okay, but I'm not in that stage, or I'm not in that particular mood to follow these very strict, very exhausted requirements. And one thing he pointed out here is that what I'm doing, the original VHDL code I wrote was in, I think, in the year 2000. Okay. And what I used was a 1997 IEEE standard library. And this is outdated, okay? And he pointed out that there are much newer library available. And I was still using the old syntax, old command. But he cautioned me that if you want to do it right, have to follow the newer standard released in 2010. Okay, Testbench can be an effective means of verifying an HDL design, often more thoroughly and quickly than by running the application. A Testbench can verify in corner cases and special cases where it might be hard to test via an application. That's what I'm doing, okay? I have a fourth as an application, and I use this application to verify the design. And of course, you can see I have not traversed the entire design, testing everything. And since you don't test, you have no assurance that it's correct. It can even verify by exhaustive coverage of all inputs to a module. Running a range of test cases with automatic verification allows large runs to be completed without user monitoring. A test bench can be designed to completely verify requirements. So that's the industry. Okay, if you want to do the chip design in the industry, follow these guidelines. But what we fourth people try to do is always cut corners, okay, to see what we can get away with. That's what I was doing. Okay, I'm sorry about the bugs in it, but I think it allowed me to do a project and see the results much earlier than you are following the strict rules of approach. Yes.
Kind of follow up that question I just had. So if you only use half of the primitives, then can you write a test bed just for those? Or is the test bed based on all of the primitives?
If you design a test bench,
that's okay.
Yeah, you should try to test it exhaustively.
Okay.
Okay. And I'm trying not to do all the work, and I try to do the least amount of work to verify that I have a usable design. But I think I cannot go out and sell it. Okay. If people paying real money, they want assurance that this thing is going to be correct in all cases. Okay. Any more questions, comments? Yes.
Has written similar test benches for any other CPUs?
I don't know. I think he. It looks like he did it for all his life. So he must have done many more projects. Any questions? Any comments?
With your own processor,
Yes.
For the P16, presumably you've been doing this for years, so you don't need to have a test bench for the P16 because all of your primitives are in. The fourth primitives are in.
Yes. The for the P16, because I'm quite sure of the correctness, because in the fourth system I've used all the instructions. Okay, because the design was to see the least amount of instructions necessary for a computer to run, and we only put in those instructions that we need.
Is the lattice board capable of running P32?
Yes. I first did the EP32
right on the Xilinx chip.
On the Xilinx, and then move on to this one. and later I trim it down to 16 to make the EP16. Yes.
The EP32 and EP16, you had EXE to play the commands, so you could do a lot of testing on the EXE.
For the EP16 and EP32, we only all the instructions are there because we need to use them. The force is running, it verifies all the instructions.
So you had the EXE file for the WE4. Are you planning to create one for EP8080?
Well, this is the force that I use to compile the assembler.
Oh, okay.
To assemble the E-force system. Okay.
Yeah.
So we are not. This is a force system for Windows that I use to do the assembly.
Okay. So it wasn't an emulator.
No.
Okay.
No. It's a full system for Windows. Okay. Then what I want to do is to go over the last month I talked a little bit about the design, but didn't have time to go through the all the historical processors. Okay, I was trying to last month. I thought that I would have, if I can talk about these things, and maybe you guys will pick up one to implement it. Okay, but so let me just go through this the first part of it really quickly. So the workshop is basically Diamond IDE system, and then the Bravia. Okay, last month I was working on the 8086, tried to trim it further down to the most concise description of a force system. Okay, and then I wanted to review the CPU architectures. So let me just quickly run through what I like to talk a bit more of those CPU architectures. Okay, synthesis. If you want to do the EP80, you have all these 5 files that you want to put in your project. And if you click on the synthesis tool, it will take these files and then synthesize the whole design. And it can recognize that the EP80 underscore chip is the top level because it calls everybody else. Okay, so the IDE is really quite nice. Lots of things you don't have to worry about. It takes care of the files automatically. So you download the FPGA image, and then if you have a hyperterminal interface, you can verify that the E-force is really working on the 8080 chip. So we need to do the assembly. Another very interesting feature in the Diamond IDE is the review. So, you know, it is like an oscilloscope. You can have an oscilloscope to look at all the signals, not only the input-output signal, that's what the real scope can do. It allows you to look at all the signals inside the chip, which are not available physically. So what this review allows you to do is to insert certain logics in the design so that it will record the signals for a period of time. And you can stop it and then examine the signals. You can actually set up the trigger conditions so that it will stop at a certain point, and then you can it will review all the internal signals that you have selected. But this, you have to use the review inserters telling it which signals you want to record, and then do the synthesis. This way, the review logic, the recording, will be synthesized with your CPU. And once you have that thing inserted, you can use a review analyzer, just like a scope, to look at the signals. So these are very interesting things that if normally you can kind of figure out the problem with the simulator. In the simulator, you can see all the signals, and you can do all the verification that way. But there are cases that the simulator is not able to tell you everything, and only when it's in the FPGA, the problem showed up. What do you do? Well, review logic allows you to look at these things. So I'd like to talk about these various CPU architectures and show you that there are very interesting things that you can test them. You can play with it, actually reduce them into physical design. So the cardiac computer, this is the computer on a cardboard, on a piece of cardboard paper. Okay, so the CPU is you, okay, and it basically it's a three-digit decimal computer. The memory, it has 100 cells. Each can store 3 decimal digits. It has an accumulator, 3-digit accumulator with a sign, an extra sign bit. 1 input port, 1 output port, and it has only 10 instructions. Okay, so this is what it used to be on a piece of cardboard paper. So you write the instruction in these cells. Okay, there are 100 cells, and you can write numbers in it. The numbers can be data or can be instructions. And here, this is a simulator. Somebody wrote on Excel. Okay, so you can see these are Excel cells. Okay, and this column is an input, and this column is an output. So when there are 10 instructions, input, this instruction read what's in the input register. Clear A, clear and add. Basically, it just load a number into the A register, into the accumulator. Add, and well, test accumulator contents. Shift, output, store, subtract, jump, halt. Okay, 10 instructions. So I think that this should be very easily done in VHDL, okay? And that kind of challenge you guys to do it. Because 10 instructions, that's very, very simple to do. And it has only 100 cell of memory. What I think for a modern design, you know, the decimal numbers are not appropriate. Okay, it's harder than binary. So I would challenge you to do a design using 3 bytes for memory. Okay, 1 byte for instruction, and then the 2 bytes for the address. Okay, and then you know 10 instructions, or you may want to implement 16 instructions or more, whatever. So it has an accumulator. The accumulator has 3 digits opcode, X and Y. Okay, the opcode you have 10 opcode. Okay, and actually it's a very amazing that this very simple design actually allows you to do very complicated math. You know, multiplication and division. These are 2 obvious examples. Square root is going to be more difficult, and maybe sine or cosine. Okay, so all these things, just with this 10 instructions, you can do a computer with a very limited amount of memory. You got quite impressive math. Okay, so this was originally a piece of cardboard paper. I think John Ribel probably still have a copy of that cardboard computer. So I think as he told, he was an MIT graduate, and he was even before he entered into college, in high school, he was playing with this cardboard computer, and that, I think he learned computing that way. So lots of people are doing it.
I have one, but I can't remember where I would have gotten it.
Yeah, it's going to be an antique, you know. But now you know that if you search the web, you can find that simulator on the Excel. Okay, it actually you can put numbers in, and then you can watch the thing running. But I think the challenge is to implementing VHDL. The interesting thing about the input and output. So it has input port and output port. Okay, so you can read input and generate output, and that way you can. I was thinking of doing a 4th for it, but not doesn't have time to think it through. Okay, now this is the first real computer. Of course, the first real computer was ENIAC, but ENIAC was designed by a couple of engineers who really didn't take a first course in computer science, because at the time computer was not a science; it was an engineering project. So what did they have is 20, I think it was 20 decimal digits. It has 20 registers, and each register has, I think, 20 decimal digits.
Yeah, that's what the Wikipedia said.
Okay, yeah. So that was the, and the von Neumann, when he got invited to look at this this computer, he thought, sucks. So he went back and wrote a report, and talking about how a computer should have been designed, using binary using you don't have to have a separate program space versus data space. You can combine the, so these are the original design. So the von Neumann design, it uses 40 bits binary words, basically to compete with this 20 decimal digit computer. So it would match pretty much the same range. It has two registers, AC and MQ. AC is the accumulator, and MQ is basically for the multiplication to store the quotients. Okay. So when you do multiplication, you actually has 80 bits of product. And in the 40-bit binary word, it divided into two instructions. If it's storing instructions, you have two instructions, two 20-bit instructions, and the 20-bit instruction has a 12-bit address and 8-bit opcode. So it can address 4,000 words, 4,000 40-bit binary words. And it has, using the 8-bit opcode, he only implemented 21 instructions. So this is the general architecture. So you have ALU, and then the accumulator and MQ register. And everything else is from the memory. And the instruction slash there, IBR, I don't know what it is, and the program counter. So it is a very simple architecture. And the instruction, let's say 40 bits, and the left instruction and the right instruction. So the left opcode and right opcode, they are 21 instructions. I think these are a very good design and very concise, and it does almost everything that you would ever want to do, except he didn't know the stacks. Okay. He didn't know the, I think, knows the subroutine. He had recognized that programs should be designed in modules in subroutines. But this architecture makes calling subroutine fairly difficult. But this is the granddaddy of all. And then IBM, when they do the real computer, they took the exact architecture and implemented in their first 701 computer. It used 36-bit binary words and two registers, AC and MQ. And the instruction set is it uses 18 bits instruction, just like the von Neumann machine, 40 bits divided two. It has 36 bits and divide them into two 18-bit instructions, 6-bit opcode and 12-bit addresses. So the same address for K, but it only uses 6-bit for opcode. And it has 33 instructions. It should have only 32, but I don't know. It has something added to it. I'm not quite sure. But generally, it is the same kind of thing. But it has the, I think at the time they have the tape machine, the tape drive. So it has rewind, write, and write end of file and all these things. So these are what's required for a big computer, unlike what IBM would do. So 701 took the von Neumann architecture and turned it into a fairly successful commercial machine. I think 10 years later, IBM changed the architecture and actually did a modern computer, deviate from von Neumann. And the 360, the memory is 32-bit, because at the time I think people recognize 8 bits are the most natural subdivisions of the binary words. It has 16 32-bit registers and 4 64-bit floating point registers, 8-bit instruction opcode, and the instruction set, instruction is 2 to 6 byte variable length instructions. So it has integer instructions, BCD instruction, and floating point instructions. So this is the first of the modern computers. And let me see, is this anything? Yeah, 16 general registers and 4 floating point registers. But 360 is much more complicated. This is only the CPU part. But IBM has lots of other things built around it. Of course, this is instruction. You basically have an opcode there, and then depend upon the instruction, it has arguments following. This kind of reminds you of the Intel 8086 architecture. Okay. So, all this computer, if you look at just the CPU part, they are not hard. Instruction is the instruction set is quite limited, so it shouldn't be hard to put into VHDL. PDP-1, okay, that's the first mini computer, and the story has that the DEC built the first one and gave it to MIT. By giving it to MIT, it actually realized about 80,000 profit, because PDP, the building cost, not the design, just the material building cost is at the time of $40,000, but they are selling it $120,000. So they gave one to MIT, and they wrote off $120,000 and making 80,000 profit by the donation. And then they get all the software from MIT. So it's still a von Neumann architecture. 2 register AC and NQ, 18-bit instructions, and it has the 5-bit opcode, 1-bit indirect, and the 12-bit address. So I think the indirection is the major advancement. Let's don't worry about the details. But the instruction, PDP-1 instruction, it's an 18-bit instruction. You have 12 bits of address, so it addresses 4K words, and a 5-bit opcode, so you have all this opcode, and this bit is an indirection. If this bit is set, the address is the content of, okay? It's indirect. And the interesting thing about this bit is that if you go to the memory and read one word, and if this word has this bit set, it's another indirection. Okay, and so forth. Okay, there's no limit to it. Oh well, I think the first time I did it, but I thought no, I cannot do that, because in memory, this bit are often used. So if that's an indirect bit, then I cannot write my 4th code. So what I did is that this indirection is only valid in the instruction. It allows only one level of indirection. So
18-bit words and the memory is word addressable.
Yes. It is the word addressable. Yeah, right. So only 4K words. Okay. And it's only in the PDP-8 they get around that problem. So all the, you see, except of course the 386, IBM 386, they broke the 4K word boundary. But all the other architectures, the address in space is only 8K. And the PDP-8 trims down the PDP-1 to 12-bit. So it is a 12-bit core memory. And register still have AC and MQ, and 6 regular instruction and 3 microcode instruction. So it has. Let me show you. Okay, so this is one of the pictures. I don't think I want to. The interesting thing is the instruction set. So you only have 3 bits for opcode. Okay, and the offset. The offset, I think, so 3-bit. This is a 12-bit instructions. 3-bit, you take out 3-bit, 4-bit. So you have 8 bits there, and 7-bit for the offset. And I for indirection. M is a page select. Okay, if M is 0, you are addressing 0 page. So that's the first 128 words. And if M is a 1, then this is the offset. This address is offset to the PC. Okay, so you can address plus minus 64 in the memory space. And the indirection, of course, is the if I is set to 1, what you have, the address is not the address, but the content of it is an address. So this allows it to work out the, it breaks the 4K boundary. So the, I think PDP-8 can address 32 or 64K of memory. The problem, of course, is only it only has 3 bits for the opcode. So it implement and PAD. It's just load into accumulator. ISZ increment and skip if 0. DCA I forgot. Jump. JMS probably is a jump to subroutine or something. So you have only 7 instructions. You are only allow 8 instructions. So it implements 6 instructions there. And then when the 110 is an IO instruction. And the 111, then it uses the bits to specify detailed ALU operations. So this way you only have 3-bit instruction opcode, but you can implement many more instructions than just 8. Okay, and what they call it, this is the well. So the PDP-8 is interesting. Then PDP-11. 16-bit core memory, 8 16-bit registers, and it has very powerful addressing modes: direct, indirect, and immediate, pre-decrement and post-increment, memory mapped I/O, and PC relative addressing. So these are the first very modern computer with a very extensive addressing modes in reading the memory. So it is the CPU looks simple, 8 registers, and R7 is the PC, R6 is the stack pointer, and you can in the user mode or kernel mode, I think it can switch. I'm not quite sure. Okay, the instruction set, of course, much more complicated. So it has many different form of instructions. So the this instruction has a source and destination. So you can move from one place to other, one register to another, or one memory to another memory. Very powerful. And then the multiply, and then you can include some displacement in the opcode. So this is what that complicated instruction set computer would look like. But I think it should be, the most important or the most difficult task in designing this computer is to take care of the addressing modes. Okay, so if you can do the different addressing modes, direct, indirect, immediate, post increment, and pre-decrement, post increment, and all this. If you can design that address calculation unit very efficiently, this thing should be quite easy to do. Okay, then at the same time, with PDP-11, data general, the two engineers in DEC, they got an extremely good design, and they talked to the management. Management is, nah. Oh, the PDP-11 is selling like hot cake. Why do anybody want to tamper with that? So these two guys split and formed Data General and produced this Nova computer. And Nova computer actually has I think it has a very tight, very good CPU design. 16-bit core memory and 4 registers, and the CPU design is very tight. So I think it will be a delight for a CPU designer to write in VHDL. It's very, very nice. So one of the implementation, that's a Nova 2 processor. So you have the, it actually uses 8 registers inside. 4 registers open to the user, and the other 4 registers hidden. And it has the, you have registers, you have the arithmetic unit, and after the unit, you have the shifter. So after the ALU, you can shift it left or right, or you can exchange 2 bytes. Okay, any results from the ALU, you can shift, and you can also swap. And then it has a no-load switch that the result you have the option to load it into a register or not load it into a register. And why do you want not to load if you do all the work in the calculation and shifting? But I think it's quite useful in having the option of not loading the result back into the register. So very nice, very tight. And the 16-bit instruction you have the you have a source register, you have destination, you have the function, and you have the shift, and you have the no load, and you can skip. So all these things are done in a single instruction. But it's beautiful. And of course, you can have other format, and which will do other things. But I think for the CPU, for the ALU, this is the best ALU design. Of course, now get into the real modern world, Spark and the MIPS. They start the RISC revolution. 32-bit instructions and words. It has 32 registers, load store, and 5 types of instructions. So, MIPS supposed to be minimum instruction set computer, but it's very complicated, and it gets more complicated as time goes by. So I really don't recommend you even look at these things. And I can only present you with this very simple block diagram. You can integer unit, you can floating point coprocessor unit, and inside of it, horrible. But one of the very interesting is the stack, the register windows. We have 32 registers. 4 registers is global registers, and then input registers, local registers, and output register. So if you do a window switch, you use the out. Actually, here, the output is mapped into the input register of the next window. So I call in one cycle. You just move all the output data into the input data, not actually shifting anything, not actually moving anything. So that was very interesting. But using 32 registers for any of the subroutines, nah. I don't think any people have ever wrote any subroutine which uses 32 registers. So it's all the ways that you have, and that in fourth, 32 register is enough for either the return stack and the data stack. So you only have 32 registers, and you can implement it one computer much more efficiently than what you see here. So the instruction set, very complicated. Don't even want to talk about it. Okay, MIPS, same thing. Okay. Okay. Well, we have to pay due respect for MIPS because the president of Stanford University was the original designer. You can't badmouth him too much here. I think is he yeah, he had retired already, or okay, this year I think. This year. Yeah. Mm-hmm. December. Mm-hmm. So the ARM 32-bit instructions and 32 registers, load store, 5 type of instructions. Very much the same architecture like MIPS and Spark. So, well, the instruction format, 32-bit instructions, source and destination. And if you need the third register, usually it is specified here. And conditional, that's a big waste, I think. So you have 4 bits to specify whether to execute this instruction or not. Okay, so it is very powerful. If you have occasion that you need to do it, it's very very powerful. But just imagine how many instructions that you want to do conditional instruction when you write a normal program. So this 4-bit is generally waste. And but well, that's the best-selling microcontrollers so far. Every cell phone has one. What can you say? But all these MIPS, Spark, and ARM, they are very nice force engines. Okay, and they if you don't need all the features, but it's implement a force engine with this instruction set. Generally, it's quite pleasant. Although although you don't use all the facilities that's provided. Okay. Any questions? Any comments?
Where would you put things like the J1, things like that, or the Novix?
Beg your pardon?
Where would you put CPU J1 and the Novix and such? A whole nother, maybe.
No. I think Novix is very similar to the MIPS. I think, yeah, very similar. Okay. But the Novix is much more micro-coded. So generally, it try to use all the bits. So one instruction you have many bits, and these bits all do different things. So I think that's a very nice instruction set. But it's still very complicated. So I think, of course, my preference is the MUP21, and well, Chuck has reduced the instruction set to about 23. And these are the instructions that you must have, okay? And all the other instructions in any of the architectures are optional. Sometimes it's useful when you need it in particular cases, okay? But you don't always need them. You can do without. Okay. So in that sense, I think the MUP21 and then the EP series, we try to get to the bottom of it. Okay. What we asked was, what can you do without? What do you have to have in order to get a computer going? So these are the things we have. Chuck has distilled the instruction set to the minimum, and this minimum can be implemented very efficiently in hardware. Okay, and I think one of the very powerful feature of the MUP design is that the subroutine call and subroutine return these are all one cycle instructions. And the looping, to do a loop, it's also one cycle. And none of the other designs can do that. Yeah.
Have you followed the RISC-V group at Berkeley?
Have you followed the RISC-V group at Berkeley?
No. What is it?
It's an open source modern chip design project with the idea of a open source chip that you could burn on. I hope FPGA compatible.
Yeah. I'm sure it. Okay.
There's several. If you search on YouTube, you
okay.
can find. You can watch lectures about it, which are fairly easy to watch and interesting. And
so it is the basic 32-bit words.
I'm sorry, I don't remember the details. But one thing they've done is they're using a functional language to design instead of the traditional Verilog or whatever. And they talk about the extra benefits in tools that you can automatically generate from having a nicer design language.
Yeah,
and I thought that was interesting.
Yes, that's right.
Reminds me a bit of some people are doing the dependently typed language for hardware design, so you can verify like the same way you verify a theorem or so on.
I think that's what they're talking about, yeah.
But it's baked into the hardware design language. So you don't need to do like test suites and run over all these test suites, but you have to prove your way from A to B basically.
Oh, okay. That may be a stronger typing approach. Yeah. Okay.
Yeah. I think the approach that I'm following and I encourage people to follow is that the CPU design is not enough by itself. Okay. You have to consider the software and to run on this thing. Okay. And you might just well write an operating system. You write an assembler, write a compiler. Because without these things, just a CPU is useless. Okay. So I think when you design things, you have to think what am I using it for? And I think fourth is the simplest operating system, or the debugger, or the test bench, for that matter, that you can build together with a CPU. Okay, and I think the exciting thing about this Bravia kit is that it has the the Xilinx chip. Was very powerful, very fast, very big, but they need an external device to store the design. And when you power up, this design has to be moved into the FPGA to make the circuit work. And this is not safe, okay, to say the least. But only in the Lattice FPGA, they have enough flash memory inside to store your original design in it, and they have extra flash to store your program. And this way, you can put a whole design into a single chip without any other things that the thing the chip would run. Okay, not just run by itself. It also has the program just sitting along with it to to do your application. So I think this is the most exciting thing that, and this is what we are running this workshop now, because now you can do everything on this little kit. I have talked about this story before, but I want to repeat it because I think it's very relevant here. In the late 1990s, when Chuck was designing the MUP 21, at the time he was living in up in the mountains and Woodside. So we took the design. He did the design. He put the drawing out, and gave me the design on a floppy, 3-inch flop, 3.5-inch floppy, and I took it to the fab. What was that? Orbit. Okay. So Orbit would put that design onto 20 chips, and after 2 weeks, we get it back. And I took it there and drove up the mountain and gave it to Chuck, and Chuck would find a way to test it. Okay, it's amazing that he only with one oscilloscope, he was able to verify that chip, and he wrote small programs to run on the chip. And so, during time one afternoon, I was sitting there. And Chuck was dreaming, and he said, "Wow, I wish that these companies, they are just cooking the silicon, right? They take a piece of silicon, do something on top of it, and then bake it for how many minutes, and then you got a chip. So I wish I have an oven like the microwave oven you have in the kitchen. You put your chip in it, you dial half an hour, and start, and it run. After half an hour, the alarm sounds. You open it up, and you take out the chip, and you can test it, you can run it, you can do things. So that's what was the dream, because that was what we're doing. We have a design, and we cannot have a microwave oven to bake the silicon. Have to have somebody else do it for us. But that's essentially what they are doing. They bake the silicon chip. So, Chuck was saying, if I have a microwave oven, I just bake the silicon chip and I get my chip. And now we have it. Okay, we have it. We don't even need the microwave oven. Okay, you have it there. Okay, and you can do whatever, put whatever design in it, and in about 10 minutes, you got a new chip, and you can see what it's doing. So this is what really excited me, and I hope to share this excitement with everybody, and hope that you will take advantage of this $50 kit and put your mind to it and make something useful. Okay, well, thank you very much. I think it's a lunch break. Okay, for people out in the real world, see you in the afternoon. Bye-bye.